Welcome to today's Jones seminar. Our guest today is Professor Srinivas Tadigadapa. Srinivas Tadigadapa is a professor and chair of the Department of Electrical and Computer Engineering at Northeastern University. Prior to that, he was a professor at Penn State in the Electrical Engineering Department, and his primary research interest is in microelectromechanical systems, or MEMS, and the design, optimization, fabrication, and testing of MEMS transducers. Now, more specifically, his focus is on fabrication of novel micro and nano sensors and actuators by integrating non-traditional materials using silicon microfabrication techniques and exploring phenomena at the micro and nano interfaces. He has published over 200 peer-reviewed papers and is an inventor on 10 patents. He was awarded the Alexander von Humboldt Fellowship in Germany, the Science Foundation Walton Fellowship in Ireland, and the Meritorious Service Award from the IEEE Sensors Council. He is a fellow of the IEEE, a fellow of the Institute of Physics in London, and a life fellow of the Cambridge Philosophical Society. He is also the founding editor of the IEEE Sensors Letters. And so with that, please join me in welcoming our guest today, Professor Srinivas Tadigadapa.
Thank you, Kofi. Again, I am absolutely delighted to be here, and thank you for the invitation to come here. Yesterday driving in, I didn't realize that I would be choosing the best time of the year to drive here. The weather too worked. So what I will do is I will tell you of some of the non-traditional fabrication that we are always been engaged in, and talk to you a little bit about micro-resonators. I may have more slides than I will be able to deal with in this 1 hour that we have, but we'll see how it goes. But before I go anywhere, I have to do the job of a chair of a department, which is to kind of tell you some things about the college and the department. So the College of Engineering at Northeastern has been growing quite rapidly over the last few years. We have 5 engineering departments, all the main engineering departments, and it's fairly big with about 215 faculty in the college. In particular, though, electrical and computer engineering is also a very large department that has been growing in the last few years. We now have 75 tenured or tenure track faculty and another 21 research and teaching faculty, so about almost 100 faculty at this point. And in the last few years, we've been averaging about $40 million plus in research funding, so it's actually quite a healthy research institute now, or department, I should say. So without doing anything more beyond that, I will now start probably to set the stage for the talk. So why, I mean, as an electrical and computer engineer, the last 70 years, all of you know, almost till about 1980s, 1990s, continues. We call this the era of computation, which is basically where we started with the ENIAC computer on one end, and we've gone all the way up to the other end with billions of transistors on a chip. Somewhere in the 1980s to 1990s, we have come in. Electrical and computer engineers have been very instrumental in the next revolution, which is the era of communications. And it is continuing almost till today. I mean, you know, 5G, 6G, we talk about, it's all happening because of electrical and computer engineers. And now, at this time, we are moving into what I call the era of cognition, or engineered cognition. So we are continuing to be at the forefront of a lot of the research that is happening and a lot of the innovation that is happening in the world. And when I call the era of cognition, what I'm really meaning is that at this point, we are not talking about the sensors. We're not talking about communications. We're not talking about robotics. We're talking about everything together, integrated with machine learning and artificial intelligence, and At the end, we don't want machines to be, just switching on and off. We want them to be making decisions for us to some extent. And that's where we are headed. And this is the next era that you will be working in as I see it, with a mixture of all the hardware and software that we've put together over the last several years. So with that kind of a broad, kind of introduction to electrical and computer engineering, I'll come back to my area, which is my area of specialty, which is MEMS and microelectromechanical systems. And again, 30 years of lots of sensors and devices have been made using these on-chip micromechanical devices. And these include, of course, things like the accelerometers, the gyros that are present in your cell phone, the microphones that are present in your cell phones and all your noise canceling headphones and, so on and so forth. These are all mechanical devices as much as we recognize or not, and they just look like integrated circuits. Most importantly, actually underpinning many of these devices are micro-resonators. Okay, they form the core of many of these devices. So I thought that this is a nice way of staying connected to all this technology, and also a nice way of introducing you to the topic. So this comes from Umberto Eco's Foucault's Pendulum, the book. You can take a look at this, but this is anyone who has seen the Foucault's Pendulum is a very, very inspiring scene to look at. It's not strictly a resonator, but it does move with that kind of a precision that you expect of resonators. So the way it is I'm going to keep the resonators in the middle as the focus of this, and I'll start with an introduction to that, and then I will talk to you some examples of the kind of things that we have done in my group over the last several years, 2 decades or so. So let's get started with that instead of just going through a linear. These are all linked to this idea of resonance in the middle. So that's really the reason why I don't have a linear table of content for the talk. Okay, so let's start very simple, right? This is basic physics, pretty much high school if you want. So all we are looking at is a spring mass system. If you want to think about it, this is a damped oscillator which is sitting inside a damping, which is given by a quantity that will be proportional to the velocity of the part that is moving, right? And when you do this, you can actually find a resonance frequency. You can calculate for it, which is actually dependent upon, as we'll see, on the spring, the spring constant K and the mass that is there. And then there is this strange little factor, the Q factor, which I'll come and explain to you a little bit more, but the Q is essentially going to tell you how good or non-dissipative the resonance is, okay? And typically it tends to be a very large number. So the larger the number is, you can forget about it. Basically, for practical purposes, we say omega is equal to omega 0, right? And the other part of the Q factor is it is also telling us how it damps, right? So again, when you think about the bell, and when you ring it, the better the bell, the longer it rings. So that's essentially what we are doing, listening to the sound for how long it goes, right? And that's another way to look at what the Q factor is. A driven oscillator, essentially, is a case where it will stop, right? Every system will stop after a bit of damping. So to keep it going, you have to drive it. And when you drive it at the resonance frequency, all kinds of interesting things happen. There are a couple of things that I would like you to keep in mind out of all of this. One is how much of energy you have to keep spending to keep it going as a resonator. But the more other important thing that I want you to look at is this particular equation here, this part here, where I write the amplitude is actually given by the static amplitude. The static amplitude would be that you pull a spring and you know, depending on how much force you apply, you get the spring to stretch. So that's just the basic static amplitude. But in this particular case, it is amplified by the Q factor. I remember I said to you that the Q is a very large quantity, typically. So as much as it doesn't affect the resonance frequency, it is going to amplify the amplitude. We know this, right? This is the problem that soldiers on the bridge that we get told in the basic physics problem, right? That bridge is broke, and so we try to avoid the Qs and so on and so forth. This is exactly, but this is to an advantage, okay? You think about anything in real life as a measurement. You think about measuring an amplitude, typically. And the amplitudes are difficult to measure. You think about voltage measurements in a lab. Try to measure a microvolt. It is not that easy. You'll suddenly be facing noise of all kinds. And since these are low frequency, typical, measurements, you really are impeded by what you can do. On the other end, if you convert whatever it is into a measurement of a resonance, okay, now you're getting the amplification of the Q factor. So suddenly, what was just a microvolt, I could make it 1,000 times bigger, or a nanovolt. And suddenly I have this possibility to measure much smaller frequencies. Not only just that, I am also at resonance, which means I have a particular frequency that I'm looking at, which means that I can narrow my bandwidth, which means that I can forget about noise everywhere else, but just focus on that one frequency, which is the resonance frequency. So suddenly, after almost 15 years, 10 years of research, one day it dawns upon me, I've been wasting my time measuring analog things in the analog fashion. I should just move towards the resonators. And that's really the wake-up call that I've literally followed. And so I continue to do that till today. Before we go in, I'll just kind of talk a little bit about the Q factor and how we define it. It is defined as the full width at this point, which is the half of this peak here, the resonance peak. So we call it the full width at half maximum. And that's one of the definitions. But a better way to look at it in the frequency domain and in the time domain is, do you basically have an oscillator you switch off at a certain time and watch it decay down in time, and you find what is the characteristic time at which the amplitude goes to e to the power minus 1. That particular time is the decay time for it. And so once you know that time constant, you can figure out the quality factor. So higher the quality factor, the higher the amplitude, the sharper the resonance. This is the important thing. And almost in all measurement cases, you do want to have a very narrow and very high resonance, if it's possible. Now, there are cases where you probably do not want it, but we can talk about it separately. I'm not going to cover that in today's talk. So the first one I'm going to do is the one that I'm working right now these days in. This is my favorite one because it's just fun doing this research, okay? You have to understand that research can be quite fun if you are working on things that you really enjoy. So the whispering gallery mode resonators is what I want to come to. And this comes from, actually the word comes from, a long time ago from St. Paul's Cathedral in London, where Lord Rayleigh was doing some simple, experiments, if you wish to, where he found that you could be on one end of the gallery and you could whisper, and people on the other side could hear it without any problem. It's a pretty large dome, if you've been to the St. Paul's. And so you normally should not hear it otherwise, but you can. And the reason is the sound skims along the dome and then makes it to the other end. And so this is, of course, an acoustic wave in this case. So what we were interested in is trying to do an optical analog of this. Okay, so what we do in this particular case is that we take a little laser light and we essentially use a tapered fiber, just a fancy word for just saying that we make sure that we strip the fiber off, and so that there can be some electromagnetic radiation that can leak, and then coupled to this particular resonator, which is shown as a sphere in this case. And then the idea is that once it couples in, light gets trapped inside the glass, and the glass acts as a fiber by itself. So the light kind of just internally reflects going round and round. And like anything else in resonance, if you can make the number of rounds to be an integral multiple of the wavelength, you can interfere constructively. Every other wavelength will not interfere constructively. So when you scan with a laser frequency, wherever that condition is met, you start getting constructive interference and you get resonance. So basically, you absorb the light from the laser and it goes into your resonator. And that's why you will see this in the form of a dip. So that's really the basis of this. And you can, once you have this, so that this is the resonance condition, the first equation, which is what I said. So 2 pi r, or n is the refractive index of, in this case, the material, whatever it is equal to m, which is an integer, and lambda is the wavelength that we are looking at. There are a couple of other things that you have to look at. So there will be many, many modes that will satisfy this. So it's not like there's only one M. So you're looking at one mode and the next mode. If these modes tend to be very close to each other, you'll have a little bit of difficulty in separating them because one will hop to the other and back. So you want these modes to be separated far apart. One other way of looking at it is that you want the Q factors to be very, very high. The higher the Q is, the sharper they are. And so therefore they will be better separated even if they're close. Limiting case being a delta function, which would be just a spike, right? And so there'll be nothing then, I mean, in between. So the finesse is another way of looking at how the Q factor versus the separation of the modes is. This is just me giving you a very quick, introduction to these topics. So you can see a higher finesse is a better, separated resonance as opposed to a lower finesse, which means that the quality factor of that resonance is higher as well. So that's just the ways to look at it. And you can actually go in and do the entire simulation of looking at the different modes. This is the wave equation, which is a partial differential equation. And you can, in this particular case, it's a spherical structure. So you will be solving this in the spherical coordinates. And those of you who have done partial differential equations, you know that if you have 3 dimensions, when you do separation of variables, you are going to end up with 3 constants that will come out as part of the eigenvalues. And so you end up with 3 quantum numbers or 3 numbers that you will need to do the separation. So the S, M, and L are essentially the radial and the azimuthal and the polar angles that you're getting the quantum numbers from. Not going into too much of detail, all it means is that for every principal quantum number, you're also going to have these other quantum numbers that you could look at. And so basically you can look at the wave as it is interfering, how it is traveling for every of these modes. And we can actually do these type of simulations using simple multiphysics console modeling. Okay, so the fun part, right? So all this part was okay. The idea was, can we do this on a chip? That's where the fun comes. That's where the non-traditional fabrication comes, right? So our idea was, yes, we should be able to blow glass. After all, it's not only the Italian glass blowers where we go and pay tons of money to get all the fancy stuff. We should be able to do this in the lab. And that's really how we got started as Curiosity Project. We take borosilicate glass. If any of you have a chance, you can go to the Corning Museum and you can actually blow glass there too, not too far away from here. And it's literally that. It's just that we do this on a chip. So we use what is called as an anodic bonding process by which we bond glass to silicon with no other material but molecular bonds that will happen between glass and silicon. Once you do that, you have a cavity that is, say, pressurized. In this case, say 1,000 torr or something like that, a little over atmosphere. And then you heat this up very rapidly so that the glass starts to become soft. Borosilicate glass, melts around about 500 degrees Celsius. Beyond that, it will slowly start becoming liquid. And now the pressure in the chamber has gone up that little cavity, which because of temperature, right? And so it starts to push this glass outwards. And the glass does nothing but expand to become a nice, beautiful spherical bubble right there. Okay, and so the nice part of this is that it's a blowing process. So because it's a blowing process, its surface is nanometer smooth. If you try to microfabricate these type of resonators out of glass, you'll end up with the etching processes, which will be not so perfect atomically. But because this is just a nice, beautiful expansion, you can just make it how you want. And so it took us some time. I have to admit that it was not like the first blowing looked like this. I make it easy by telling you how it is. And so you can not only just do one, you can do many if you want. And so suddenly, just like you make transistors on a chip, you can make bubbles on a chip, right? We can make donuts on a chip if you want. We can do anything with this. We can make complex glass microstructures, but then you need microscopes to see those and admire them, okay? But they're fun. So the nice part was, once we got these are very thin shells. We can control their diameters. We can control the shell thickness by playing with how much of glass we have, how much of silicon we have, or the cavity we have, the pressure. And basically by playing with the process, we can create all these kind of structures. So I'll kind of tell you a little bit about one of these structures and how we then start thinking about sensors with this. Okay, so you use a tunable laser. In this case, it was a 760. That's how we started this project. These days, we use a 1550 nanometer. Glass is transparent. We all know this, so it is the right material with visible. You can go almost up to 2.5 microns, which is infrared, near infrared. It will be still transparent. But once you reach 3 or above microns of radiation, glass becomes opaque. It's kind of weird to say, but glass is opaque for all those other wavelengths. And you can also see that the energy is confined on the equatorial plane, just like I had drawn in the schematic, by seeing that the light is actually just only in the equatorial plane. So we start looking at all these resonances by doing these scans, and when you look at them, they just look like all these sharp dips. These are all the dips where the condition for resonance is met. And as I said, they correspond to different modes, so you can pick your mode carefully so that it's well separated, and you can get some very high quality factors. So if you look at the quality factor for this particular device is 52 million. So I told you Q is large. So don't expect every system to have a Q of 52 million, okay? Only optical devices have this type of Qs. If you have a mechanical system like the one I showed you at the beginning with the spring, or even a MEMS cantilever, getting a Q of 2,000 or 3,000 will be already quite a challenge, okay? So we need to be very careful about what Q is and how to optimize that. What this means is that the light goes around this little bubble for a distance of maybe about 47 meters before which it dies. Basically, it's dissipated beyond that. 47 meters for a light that is only 1550 nanometers is quite impressive, or maybe in this case, 790 nanometers. So compared to what its size is, it travels a long way before it basically has gone away. So that's the ring down time for these resonators. So these resonators, essentially, these cavities, give us the possibility of sensing. How? Well, if the refractive index of the glass changes for any reason, right, then you will have a change in the resonance frequency. It will change the condition of resonance, right? Or for some reason, if you could change the dimension of the glass, just like by heating, right, thermal expansion, that will change the resonance condition. And so those are like two quick ideas by which you can start thinking about sensors. But the nice thing about sensing with something like this is that now you're sensitive to almost femtometer level of physical dimension change. And so because of this kind of possibility, you have some extraordinary capabilities in terms of what you can do with sensing. And there are some fun stuff that you can do that we are starting to look at. So I'll show you some of the preliminary or initial results that we've been doing in the last year or two that I will talk about. So the first thing is, well, yeah, it's nice to say that it is sensitive to refractive index. How do I know this, right? Well, fill the bubble up with some liquid, such as water, or fill the bubble up with acetone or IPA, something like this. Remember this, that we have this very tiny thin wall. You may say, well, what does it matter? Light is already confined into the glass. Why is it going out? Well, it was confined because there was air on both sides of it, or a vacuum and air. Refractive index of vacuum and air is 1. Glass is 1.5. The moment you put water inside it, you put a material with a refractive index of 1.33. Now suddenly the difference is not so much. So what does the resonator do? Well, it leaks the energy out into the water. And of course, it reduces the Q factor, but you can also see a shift in the resonance frequency for that matter. And that's really the concept here, or the idea behind. And, of course, you can see the air bubble at the bottom. But these are really tiny resonators. We are looking at an opening of 200 microns. They're about 500 microns, give or take. You can see very nicely here the fact that as you put water and acetone, you can see that it shifts. So this is the first test that you do. You kind of go, okay, well, it's working according to what we want. Well, then the idea is, can I really configure this into a biochemical sensor? And if you want to do, how do I do this? Well, a simple example or a simple experiment to do is, well, start with some glucose and add a little tiny bit of enzyme in it. Enzyme, as you know, is nothing but a biocatalyst, which means that all it does is it will take the material, glucose, to its product, but it doesn't react by itself because it's an enzyme. So we actually did this experiment a little bit differently than I'm showing you here. I'll come back to it. We do actually immobilize the enzymes on magnetic particles and use a magnet to keep them down while we introduce the liquid on the top, and then let the particles free so that they can catalyze the reaction. Anyway, as you catalyze this reaction, you wait for a while because the catalysis process produces heat, which means that there will be a temperature change of the resonator. We wait till it dies down. But what we wanted to do was to see what the refractive index does, right? So in this particular experiment, we leave it for a while, we look at the end, we see that there is a change in the refractive index. And it's a good way by which you could think about creating fun biosensors, right? I mean, this is just a proof of concept. So we started with water, acetone, and now we are saying that, well, maybe we can see reactions with it. And so that could be quite an interesting possibility. And that's what we are showing here, that we can, for example, from just this measurement, we can tell that there was a change in the refractive index of 0.24 in this particular case. We also know this, that if we will have different wall thicknesses, we can engage with the material inside differently. So these are COMSOL simulations that are just showing this. The green pictures, to be correct, are basically on a log scale, so they are just magnified what you see on the left side, okay? So the blue pictures are just in the linear scale, so no different really. But what it shows is that when you have thinner walls, you can engage with the material inside the bubble much more. You interact with it. And this means that if you want a sensor that wants to actually go and look at things on the inner surface, you want to make them with thin walls. The thicker the wall is, the lesser that interaction is, and so therefore you will be less sensitive. So there is a way. Now it gives us a handle by which, depending on what we want, we design our resonators in this fashion. And we can see that there are two resonators that we put here. These are experimental data. They kind of fall exactly according to our prediction from these type of models. So that's kind of nice. Okay, so that's the optical resonators. So that's the latest work that I'm doing right now, that my group is. I just jumped to the very old work that I did before I was even a faculty. And this is the work that was done at a startup company called Integrated Sensing Systems, which is based in Michigan. So we had this lovely idea in 1996 that if we can make a small tube and you can have liquids flowing through this tube, you can use the Coriolis Force and you can actually make it into a sensor. So essentially the way the Coriolis Force works is it's a vector force, which basically is a cross product of omega, the frequency of anything that is rotating. It's a force that is only in rotating frames of reference, and the velocity of the particle that is on it. So if you actually are on one of those merry-go-rounds in one of those, and you try to walk radially outwards while it is rotating, you will actually walk in a curve. You don't realize it, but you will do it, okay? And that's just the Coriolis force. It's just the way it is pushing you. Okay, and so the idea is very simple. If you have this kind of a resonator, if you want to think about, you resonate it, and it is kind of going essentially as a tube. It's a U-shaped tube, right? And some liquid starts to flow through it, or a fluid starts to flow through it. As it is flowing, the velocity of the fluid in this arm is facing in one direction, and on the other arm is facing in the opposite direction. So the forces that are applying on this, on the two arms, become separated. One is going upwards, one is going downwards. So what was actually vibrating like this starts to do this, okay? And if you put a capacitive sensor underneath, or basically just an electrode, gap is already there. This was the prime time for MEMS era. Everything had to be a little gap and a mechanical structure on silicon. We were excited to do this work. So, that's really how this becomes a project, right? And so you can see exactly that shape of 8, and then you start to do this. So of course, again, comes down to fabrication and creating new processes that you could. So you can see here that this was our shape of the U-tube, which is, of course, the first version at that time, which with sharp corners, but we did silicon to silicon bonding, and we made this little hole in the middle. This thing is the size of human hair with a hole through it, okay? And it is sitting on a piece of glass substrate, anodic bonding even then, okay? And a gap of only a couple of microns, okay? And then you have to evacuate it, otherwise the air that is in between the freestanding structure and the glass substrate will squeeze and will damp the system, and you will not be able to get good cues out of it. So to get a good cue, you have to do this in vacuum. But anyway, we did this, and of course, the first thing that happens is if you don't do anything, just the fact that you're flowing a fluid, the tube becomes heavier, the resonance frequency changes by the mass. So the resonance frequency itself is a function of the density of the material, and the twist is a function of the flow rate. What is nice about this is that this is an absolute mass flow sensor. This is not, so when you have compressible fluids like air and any gas, it's much harder to measure flow. Water is easy to measure the flow of because we know the density of water and it's not compressible. But with air, and it depends upon how it is getting compressed. So you can measure now compressible fluids in absolute mass, as I gave you in the previous equation. So you look at it from the twisting angle, the mass flow rate, not the number of molecules or anything like that. So I just show you some results here. I don't want to dwell too far in it, but as you start filling different fluids in this, you can see that it starts to shift, which is exactly what you expect out of the frequency. And then, of course, you have to create an interface circuit, which, of course, later on became much better, but you can start seeing the size of this capacitors. You put it into a Wheatstone bridge type of a arrangement and then look for the imbalance, and then you can look for the current from that. Eventually, this became a product, and it is actually available even today to get. This is the MEMS chip, which is the flow sensor, and with the whole electronics, it's actually a device that is a available device. Now, again, all of the things that I talked to you about resonance, I didn't go into the details of it, are all embedded in there. The reason why we can sense this and we drive it at resonance in the first place is to get that Q factor amplification that I told you at the beginning. And then because of that amplification, the change in the distance, otherwise it'll move very little. We have to apply like hundreds and hundreds of volts to just get it to move a bit. Static displacement is just not worth it. Whereas with the, and of course you got all those other benefits of density and mass flow measurement because of the resonance. Okay, so now going into a little bit different. So we went into optical resonance, we went into mechanical resonance, literally on a chip. So the next thing that I'll talk to you is actually an acoustic resonance in this case. It's an acoustic device, and again, comes back to the fact that I don't work necessarily with silicon. Silicon is just my ruse to work with other things. So what we were looking at is quartz, single crystal quartz. So as it happens, quartz is one of those materials which is, very well known. In fact, Madame Curie found the piezoelectric effect in quartz. That was the first time we came to know of this effect. So it's a very old and well-known material, okay? However, quartz has done one thing, and it has defied the fact that we, as engineers, have been unable to deposit it as a thin film to date with the crystal structure that maintains the piezoelectricity. And piezoelectricity comes from the fact that these are crystals with a particular structure whereby there is an imbalance in the charges of the positive and the negative ions inside the molecules. We just can't get the axis, the C-axis of the quartz to align when we deposit. We can grow the crystal by the traditional methods, but we cannot put it as thin films. It's quite different from aluminum nitride, which we also knew, but 20 years ago, we were able to develop a process by which we can actually deposit aluminum nitride in piezoelectric fashion. But anyway, I will not go into aluminum nitride for the moment. Let's just stay with quartz. And quartz is then, if you then take a quartz crystal and you start applying an AC field, you can actually excite acoustic resonances because it's a compression wave that is traveling through the material, or it could be a shear wave through the material. You can actually start having two boundaries, which is the two ends of a flat crystal, right? Start applying an electric field that is at the resonance frequency, and the thing starts to resonate. And that's how we have the quartz crystals running our watches, keeping the time for our computers, and so on and so forth. And so it's well known, right? But the problem with it is that, as I said to you, it was not possible to make it in thin film form. So, well, I said to myself, well, in that case, we'll develop a fab process. Now, as it happens, in that time, silicon's etching rate was going through the roof. I mean, it started at like a half a micron, maybe even a few nanometers. Suddenly, by 1990s, we were talking of etch rates for silicon that went into 20 microns per minute. Typical silicon wafer, for those of you who don't know, is about 400 or 500 microns. So that means we can actually realistically etch a silicon wafer. The question is, why is silicon dioxide, which is quartz, right, not etchable with the same speed, right? And so we started thinking about it, and we go, oh, well, maybe we'll try. So we started, and we realized that we can only etch it at a couple of nanometers per minute, which means that if you want to etch 100 microns, you'll be waiting there for weeks together before which you get down to that thickness. So we started developing a process in our lab whereby we took a machine and modified it, and we brought the etch rate up to about 1.1 micron per minute from wherever we started. And so because of this, we were able to, for the first time, really thin the quartz down and stop and make them into thin resonators that could be arrays of resonators. All right, enough of that for a moment. I'll come back and I'll close that loop on it. So when you have the resonance, just like any resonance electrically, you can actually draw the equivalent diagram for the quartz resonator. And what it is nothing but a series LCR circuit with a parallel capacitance, okay? This is called the Butterworth-Van Dyke model for at resonance. So if you actually will go and do the math on this, you know, the impedances of each of these parts, you can put them in and you can write the admittance for all of them. Then you can simplify this. And this equation, if any one of you will recognize, is nothing but the equation of a circle, right? Right? And so that's exactly what it is. So we want to look at it. So we fabricate it. Just to let you know that to get to 228 megahertz, this is a 228 megahertz resonator. To get to 228 megahertz, we're looking at 6 microns of quartz in thickness, okay? So that means if I started with 100 micron quartz, we had to thin it down by 94 microns before we can get to these frequencies. The standard resonators that you can buy in the market will be 300 microns thick, and they're 5 megahertz in frequency. So this type of possibility is because of MEMS etching and, you know, microfabrication. Okay, so we also have a very good Q factor. See, the Q factor is no more 52 million. It's only 9,000 now. There is a problem because quartz has an intrinsic limit to how high a Q factor you can get. The F times Q product, the FQ product, is limited to about 10 power 13, okay? If you will do the multiplication of 228 megahertz with 9,000, We are only an order of magnitude away from that theoretical limit of quartz. This is on a device, that is the theoretical limit of quartz. So device has its own losses beyond what the material has. So therefore, you can see that we are starting to manufacture devices that were pretty close to very good performance. And just to prove that if you really actually plot the real part of admittance and the imaginary part of admittance, that it is an equation of a circle, there it is, okay? The blue line is the experimental data and the red line is the theory. And by this, I can actually tell you all the motional components of this device. By the way, those real, that LCR circuit, those are not some real parts. They are coming from the material properties and the transduction, the electromechanical properties of quartz. And so you can link them all, including the dissipation in this particular case, the resistance, that is the motional resistance. Okay, so here's the problem with a quartz resonator. You want to do something on it? Well, the first thing that you will do is you'll mass load it. Like I told you, you change the mass, you'll change the frequency. It's a problem that you cannot deal with. Having said it, I also told you earlier on that glass absorbs every radiation beyond 4 microns. It's actually opaque beyond that. So the idea was, well, we cannot do any biochemistry on top of my resonator, because if you do it, it will just die, right? Or it'll just damp. So why not use the capability of heating it up through a very small gap, because it absorbs the radiation that comes out. And so, well, just keep it only 100 microns away, maybe 50 microns away, a reactor. So it's not mass loading, but you do your reaction there, use the enthalpy of heat, and actually let it couple straight into the resonator. And then you suddenly have a biosensor. But not only you have a biosensor, you actually have a disposable biosensor, whereby you can use this top part where I have this schematic with the little explosion going on. You can throw it after you're done, which means that you can actually use it for doing proper biomedical testing if you want to. So I was talking to one of my colleagues at Penn State when I was there, and then he was a nephrologist and goes, you know what, there is a big need for people to measure the creatinine levels in ICU patients. ICU patients come in and they basically get tested every 12 hours or so for their creatinine through blood, because they're already in a bad situation, so you can't keep growing blood off them. So 2 times a day, and oftentimes in the 12 hours that intervenes, the kidney fails, and most people who come to ICU actually die because of kidney failure. Even though they come with a cardiac problem, they actually die because of, and that's the nephrologist, not me. So I learned for the first time, and I said, oh, well, maybe we can do this. Okay, that was my first problem of some real impact or some real interest in this case. So we started doing this. This is called the acute kidney injury problem. And we said we want to make a real-time creatinine sensor that we can put in line of flow, so that when a catheter is placed in the patient, this thing is continuously looking at the urine creatinine. Up till now, the entire gold standard of measurement is only blood creatinine, because there is nothing that is available for doing this, for urine measurements. And that would be a free sample, essentially, because, you know, with the catheter, you can continuously get it. Of course, to be sure that we are doing the right thing, especially we have thermometry, we want to also do a differential style of measurement, so that we can make sure that anything that is in the environment is not starting to affect our measurement. So we basically have 2 resonators next to each other. And of course, we changed it from that little platform that I showed you before into a nice little tube. This tubing is a capped-on tubing, which is about 100 microns in wall thickness and is about maybe less than 1 millimeter in diameter, okay? And the nice thing is that this thing costs like $1 a mile or something like this. So which means whenever you will make these into cartridges, it costs nothing to do this. The main cost will be the enzyme, which we'll see, but nonetheless, the thing is not. And so you can take this and throw it away when you're done, and no more contamination issues. Our resonator and our electronics and everything else remains perfect. And so that's one of the ideas. And this is where the electrical engineer gets completely stumped, right? Because you realize I don't know any biology anymore, right? And you need to do a creatinine measurement, and how do you do this? And so we start working. I got a bioengineering student to work with me. That was a little bit helpful, but you know, it's a hard problem. Enzyme immobilization is not easy. If you don't immobilize enzyme, you're not going to be able to make steady measurements that are repeatable, okay? And so we went through the process. This is the alginate bead method. So ultimately, this was one of our problems because this would last for about 4 or 4.5 hours. But if you keep flowing urine through this, eventually the alginate breaks down. And so as it starts to break down, the enzyme goes away with it. But what we are doing is, this is called an entrapment method. So you entrap these things, the enzyme inside, and so it's like kind of caught up in this mesh. And the alginate is itself kind of porous to water flow or a fluid flow. So we basically we make these little beads and we fill this squishy beads inside the tube and then basically let the fluid flow past it in these tubes for these experiments. And we, of course, got these tiny pumps so that we can do the engineering kind of thing. So like little microfluidic, it's a little fluidic circuit, which is on a board about that size, not very big, with some pumps and valves so that you can do all kinds of stuff. Here you can see there is the resonator chip. This is the tube that is going in. The yellow tube is the real tube that I was talking about. And then there's a resonator right there. And so you can now do all the engineering fun stuff. You flow some buffer, then you flow some real stuff, and you start getting results that show the shift in the resonance. You calibrate, you start getting your results. But also, we want to be sure that we are not, just getting some spurious things. So we do the basic biology of enzymatic reactions. So we can see that we are following the Michaelis-Menten kinetics of reactions. In this case, we can pull all these constants out of this and ask ourselves if these are realistic, if we are doing the right thing. So you need to double and triple check to make sure that these things are working okay. We also realize that enzymes also, like everything else, like to function at a certain pH value for optimal sensitivity. Okay, so change the pH too far, they become insensitive. So we can see where their maximum sensitivity is, and you want to work around there. So here is the ultimate test that we did. We did a blind test. We took some real urine samples. We started testing them. We have to also measure the pH because urine doesn't come with a constant pH. So you need to know the pH of those. So that's why we have these different pHs at the bottom. It's not because it's a control sample. These were from real patients that was collected. We did the test. And then separately, my colleague got them tested at the same time with an HPLC, high pressure liquid chromatography process. And then we can see that our measurements are not that far away from the HPLC, the gold standard for essentially this type of measurements. That was very nice in terms of what we wanted to do. And so we moved, now I bring you back to the world of the microbubble again, because if after all that resonator could do it, we should be able to do this with this resonator too. Again, it comes back to the idea, right? And so, of course, these are all very temperature sensitive. We know this, 1.8 gigahertz per Kelvin as temperature sensitivity. So the idea then is why go for this resonator, right? Why do it this way? Remember what I told you with the quartz. I was forced to put this little gap, and I was forced to put this little dispensable or disposable part to it. Conduction of heat through the gap is obviously not ideal, okay? No matter how small you make it, it is just not ideal. It's just, there is resistance involved there. And so that means you're paying some price for the sensitivity there. Number one. Number two, it was great when you were working with large quantity of samples, such as, say, the urine samples that we were talking about. But there are other cases where, if you're doing any kind of protein studies and stuff like that, you're looking at 1 microliter of a protein, some expensive proteins. 1 microliter can cost you $1,000. And so you really need sensors that can also work with very small quantities of fluids. And we don't have the luxury of having big tubes through which we are flowing this. So this is the reason why we started going towards this. And the idea here was, let's take some magnetic particles and functionalize them with enzymes. Okay, and then once we functionalize with the enzymes, we can actually put a magnet and we can actually draw them and hold them tight. They don't move anymore. These are super paramagnetic particles, only a few nanometers in diameter. And then once you have the enzyme on them, you can hold them down. You can decant the liquid off the top. You can add a new analyte and let them free, and you can keep doing this test again and again. So it's a way of immobilizing the engineering way. It's not the real biological way, but anyway, it's an idea that kind of works. So we printed we have the bubble chip. We printed with a 3D printer, a cheap little thing with a small cavity in it, so that you can get about 1 microliter to 10 microliters of fluid in it. We glue the chip essentially on the bottom side, right, with a glue, and then, you know, it's basically made to be liquid tight. It's not leaking. And so now you add your enzyme, the particles with the enzyme, you pull them down, and you add your analyte on the top, let the particles free. Now they start reacting. As the heat is reacting, it just goes straight into that silicon on the chip, conductively coupling into it. And fluids are fantastic at coupling this. There's no interface resistance. And so now you can immediately start seeing much better sensitivity. And so we've done this work, and we can now get into the micromolar levels of sensitivity, probably even up to 100 micromolar. We're not done with this work, but this is work in progress. So you can now see that this resonator has a separate advantage from the acoustic resonator, which was a little bit different in the way it is. But the ideas are very similar. So these are some of these ideas we are working on to see if we can. You can also make these into infrared detectors for the same reason. Okay, you can actually, and so this is complex integration. You can thin the the quartz down, you can make them into resonators, and you put it on a silicon chip that has been pre-etched. I'm not showing you all the details, as I say here, but there's a fabrication process, very complex, but nonetheless, you can make them into arrays of these infrared sensors. The cartoons always look better than the real images, but nonetheless, they work. And that's the important point. So you can actually do the thermal time constant on these. They just work like low-pass thermal filters. You can actually do their sensitivity. And this is one of my favorite graphs, because all my life I've done many researches, but here, the blue line is a reference sensor from a company, and the red line is our test sensor. This is the only time where I have gotten a signal that looks better than that from a professional commercial company. Okay, and my students were very, like, something must be wrong. It can't be right, right? But it just tells you what a resonance does. Okay, this is my only story. Maybe I should stop here and you know, made my point. But anyway, you can see that you can, you know, configure. Once you have these things that you can micromachine, you can play with them, and you can make them into various sensors. Sometimes, maybe not. Okay, sorry. I'm not going to go then through the rest of it. I mean, this is just the same ideas. And so here is basically what we have done here is we've taken one of those resonators, made it into a cantilever, coupled it with a magnetostrictive film, med glass film, thin film. So when you apply magnetic field, the cantilever starts to bend out of plane because of the two layers. And as it bends, it induces a strain in the quartz, which then shifts the resonance frequency, which again is give you measurement of a magnetic field. So you can take the same idea, IR sensor, biosensor, and now magnetic sensor. So this is basically coupling strain into it. So here is a result, for example, of the measurement of the resonance frequency as a function of magnetic field. And here is the same measurement with a laser vibrometer, where we are looking at the out of plane bending of this. So again, proof that the device is working the way we intend. So again, I will not probably go through all of this, but you can see these as we are bending them out of plane. And there is optimization. that you can do. And the last part that I would have just spoken about, but this is too complex at this point, but you can also have another kind of resonance, which is called plasmonic resonance, which is also very helpful in improving sensitivity, especially for biosensors. So what we in my group have done is made this nanoporous gold. This is nanometer scale gold. It looks like a sponge. It really gives you like a large surface area and lots of openings in which you can get, because of which you can actually get plasmonic enhancement of signals. And what we were trying to do was use DNA binding tests. And we actually integrated this on the quartz. The mass gives you how much of DNA, and the Raman spectroscopy essentially tells you what you're looking at. And so the signal is heavily enhanced because of this resonance. Overall, I wanted to keep to the theme of resonance and show you that there are very different forms of resonance: optical, acoustic, mechanical. No matter which one you use, if you ask me, resonance is the way to measure everything. And that's my summary for you. And all I will say to you is it's just a matter of time, because everything in resonance you change into frequency, then to time domain, right? Okay, so all measurements. With that, thank you.